Greetings, and welcome to this tranquil exploration into the wonders of the universe. I am truly delighted that you have arrived here, seeking a moment of peace or perhaps a contemplative escape from the day's busyness. Whether your day has been long and exhausting, or you simply enjoy winding down with profound thoughts and cosmic mysteries rather than counting sheep, this journey is meant for you. Tonight, there is absolutely nothing you need to do but let yourself unwind, surrender to the calm, and allow your mind to settle. Let your breathing become slower and deeper, and imagine your body growing lighter, as if gravity itself has gently relaxed its grip on you. Because tonight, our voyage goes far beyond simple stargazing. We are about to drift through the vast splendor of our home galaxy, the Milky Way, a majestic whirl of stars, dust, and elusive dark matter that has been slowly turning in the dark fabric of space for over 13 billion years. Yet beneath the galaxy's breathtaking beauty lie countless mysteries, secrets that challenge our understanding of the universe. We will encounter rogue stars that have broken free from their usual paths, invisible forces that shape and influence the cosmos in ways we are just beginning to comprehend, and ancient remnants that resist our attempts to fully decipher them. Our journey will take us gently from the luminous spiral arms to the shrouded core of the galaxy, revealing colossal cosmic collisions, stars older than the galaxy itself, and phenomena that stretch the imagination. Along the way, you will learn about black holes and stellar nurseries, mysterious regions where new stars are born, and the unfinished story of a galaxy that continues to grow and evolve even now. Some of what you hear tonight may startle you, while other details could pique your curiosity enough to make you ponder long after you drift into sleep. This voyage aims not only to soothe, but to ignite a sense of wonder and discovery. As we prepare to embark on this celestial sightseeing tour, I invite you to reflect on how these calming explorations might serve as a gentle end to your day or a peaceful prelude to sleep. If such quiet, curious journeys bring you comfort or help you unwind, remember that engaging with them can be a simple yet profound act of self-care. Now, with all that in mind, let us begin. The majestic Milky Way, our home in the cosmic ocean, has never been entirely isolated. Throughout its long existence, it has experienced collisions with other galaxies, and it is destined to meet more in the future. Although it may appear stable and unchanging from our vantage point, the truth is that this galaxy formed from primordial materials, debris, and remnants left behind from cosmic encounters with smaller galaxies. Over billions of years, the Milky Way has absorbed and assimilated numerous smaller celestial bodies, pulling them in with its gravitational pull, tearing them apart, and scattering their stars into faint streams that trace winding paths around the galactic disk. One fascinating example of this ongoing process is the Sagittarius dwarf galaxy, which is currently being stretched and pulled apart as it spirals into the Milky Way's gravitational embrace. Meanwhile, in the distant depths of space, the Andromeda galaxy, a colossal spiral galaxy similar to ours, is slowly drawing nearer, inch by inch. In approximately 4.5 billion years, an unfathomably long time from now, these two giants will finally collide in a cosmic dance that will reshape both galaxies entirely. During this collision, stars themselves will almost never directly crash into one another, thanks to the vast distances between them. Yet, the overall structure and appearance of both galaxies will be forever altered, folding into a new, vast, and tranquil form, a remnant of their galactic union. Even the grandest galaxies are not everlasting. They undergo a constant cycle of transformation, colliding, merging, and birthing new structures before beginning anew. Some stars in the Milky Way are remarkably ancient, predating the galaxy itself. Not every star was born within our present galaxy. Certain halo stars, those drifting high above the galactic plane in long, tilted orbits, are relics from the earliest epochs of cosmic history. These stars, with their low metallicity and ancient origins, are believed to have formed in smaller, primordial galaxies that later merged with our own billions of years ago. The chemical fingerprints of these ancient stars tell a story. They contain almost no heavy elements, metals, as they were born shortly after the Big Bang, when such elements had not yet been forged in the hearts of stars. Moving slowly and majestically into space, they seem like elder spirits, whispering tales from a time before the spiral arms and the ordered galaxy we see today existed. In their faint light, we glimpse a universe that was younger, more turbulent, and less structured, still learning to settle into the form it now takes. Meanwhile, our solar system is racing around the galactic center at an astonishing speed, more than 828,000 kilometers per hour. That's over 230 kilometers every second. Despite such incredible velocity, this journey through the cosmos unfolds along a timeline that is often referred to as a galactic year. In terms of Earth's calendar, humanity has completed only about 20 full revolutions around the vast, luminous center of the Milky Way galaxy since our solar system first took shape. If we rewind the cosmic clock to Eris, when the earliest dinosaurs roamed the Earth, our position within the galaxy would have been entirely different. The stars that shine brightly in our night sky today were not always clustered nearby, and they will not remain so forever. This understanding reminds us of the incredible, ceaseless motion that defines our universe at every scale. Everything, planets, stars, entire galaxies, moves in a quiet, deliberate, and endless dance across the fabric of space. Even when we are asleep, unaware of the celestial ballet, the Earth continues its rotation, spinning slowly yet persistently on its axis. At the same time, the Moon gracefully orbits our planet, completing its own cycle. Meanwhile, the entire solar system is steadily drifting forward through the galaxy, carried by the gravitational currents that flow within the Milky Way itself. The galaxy is not a static entity, but a living, growing structure. Despite its age, estimated to be more than 10 billion years, the Milky Way has not yet reached its final form. It is still actively accumulating material, gas from the intergalactic medium, stars that are captured from small dwarf galaxies that venture too close, and streams of dark matter, an elusive substance that infiltrates its halo, feeding its ongoing expansion. This growth manifests not as a sudden or explosive event, but as a quiet, persistent process of cosmic infilling. Clouds of gas and dust stream inward, gradually adding to the galaxy's mass and complexity. Occasionally, this growth results in dramatic disruptions. Satellite galaxies are torn apart by gravity, their stars scattered across the sky in shimmering streams, remnants of their former unity. These violent moments may seem like chaotic upheavals, but they are also integral to the galaxy's ongoing evolution, reshaping its structure over eons. The galaxy we inhabit today is a different entity from the one the ancient dinosaurs observed, and it may continue to evolve into an even larger and more complex form, shaped by countless such events over millions or billions of years. When we look outward into the bright expanse, we see an intricate arrangement of spiral arms extending from the galaxy's core. Yet, despite our collective curiosity and longing to understand, we still do not know precisely how many arms the Milky Way possesses. This question might seem fundamental, considering that it is our own cosmic home. We would expect to have clear answers, but from our vantage point, deep within the galactic disk, the task is remarkably challenging. The dense clouds of interstellar dust obscure many distant regions, veiling parts of the galaxy in darkness, while the countless stars blend together into shimmering, indistinct patches. Over decades of observation, astronomers initially proposed that the Milky Way comprised four primary spiral arms, majestic, sweeping structures that stretch outward from the center. However, with more recent and sophisticated measurements, the picture has become more complicated. Some scientists suggest there may be fewer prominent arms, or that the arms themselves twist, split, and curve in intricate patterns that defy simple classification. Instead of neat, symmetrical arms forming a perfect pinwheel, the galaxy might resemble a complex layered swirl of stars, a dynamic formation shaped by gravitational forces that modern science continues to seek to understand more fully. Within this galactic swirl, some stars are quite stationary and follow tranquil paths around the galactic center. But among them, a small, extraordinary subset, called rogue stars, are flung from the inner regions of the galaxy at incredible speeds. These stars are nudged or ejected through violent interactions, often involving the supermassive black hole that occupies the very heart of the Milky Way. In rare cases, a binary star system, two stars gravitationally bound, can be torn apart when its members get too close to this black hole. One of the stars may then plunge inward, disappearing into the abyss, while its partner is slingshotted outward at speeds exceeding 1 million kilometers per hour. These hypervelocity stars are like glowing comets traveling alone through the darkness, far away from the bustling galactic core and beyond the familiar spiral arms. Their journeys serve as poignant reminders that even within a galaxy held together by gravity, moments of tremendous violence and upheaval are part of its ongoing story. These stellar fugitives remind us that the universe sometimes releases stars into the darkness quietly but with immense force, sending them spinning across intergalactic space and into the unknown. Such events are rare but impactful, illustrating the dynamic and sometimes unpredictable nature of cosmic evolution. Meanwhile, our neighboring galaxy, Andromeda, is hurtling towards the Milky Way in what will ultimately be a colossal collision of two giant stellar systems. From our vantage point in the night sky, high above the horizon, Andromeda appears as a faint, diffuse blur, a distant spiral galaxy similar in structure to our in the vastness of space, where time and matter blend into the fabric of the universe. The grand dance of galaxies unfolds with a slow, majestic grace. Imagine the tidal tails, cosmic streams of stars, curling outward in elegant, sweeping arcs as gravitational forces stretch and tug at each other. Sometimes, black holes at the centers of galaxies, those enigmatic regions of infinite density, seem destined to spiral closer and closer, drawn together by their immense gravitational pull, until they eventually merge in a titanic collision. Over billions of years, a span so immense that words struggle to do justice to its scale, these colossal entities will coalesce, transforming into a single, even more massive black hole. Meanwhile, entire galaxies engage in a slow, harmonious ballet, their mutual gravitational attraction guiding them through an intricate, centuries-long dance that ultimately culminates in a spectacular merger. This celestial process, this cosmic choreography, is a story written not in words, but in the movements and fates of stars, an unfolding narrative etched across the ever-expanding universe. Turning our gaze toward the stars, we observe that not all celestial bodies follow the same rules of motion. Most stars within the Milky Way orbit the galactic center in what is considered the standard direction, a unified, nearly circular dance that maintains the galaxy's structure. Yet, within this grand system, some stars chart a very different course, particularly in the outer regions, known as the galactic halo. A subset of stars moves in retrograde orbits, circling in the opposite direction compared to the majority of their stellar neighbors. This seemingly counterintuitive motion serves as a silent testament to their origins. These stars, likely born elsewhere, may have migrated into the Milky Way from smaller, companion dwarf galaxies that were later captured and absorbed by our galaxy's gravity, an event as ancient as it is quiet. Their reversed orbits act as subtle, enduring signatures of their foreign past, an ancient signature carried within their motion. In a sense, the galaxy itself is like a vast storyteller, carrying within its starry arms memories of interactions and mergers long vanished into the depths of cosmic history. These stories are preserved not in the bursts of light we observe, but in the slow, patient rotations and orbits of stars, each motion silently recounting epics of ancient cosmic encounters and transformations. The history of our galaxy, the Milky Way, is one of endless consumption and growth, but not through isolated development. Over the course of billions of years, it has grown by devouring smaller companions, dwarf galaxies, faint and often overlooked, that drifted too close, caught in the gravitational pull of the larger galaxy, and gradually dismantled. This cosmic absorption process has contributed significantly to the structure we observe today. The stars from these smaller galaxies now form parts of the galactic halo, are embedded within the disk, or are spread along delicate stellar streams, remnants of the galaxy's quiet but relentless mergers. Astronomers, through meticulous analysis of stellar motions and compositions, have identified and traced several such ancient mergers. Among them, the Enceladus event stands out, an especially significant merger that poured a multitude of stars into the Milky Way, perhaps even influencing its very early shape and structure. From these evidence, it becomes clear that the Milky Way is not a pristine, untouched spiral galaxy, but rather a complex mosaic, patched together from countless calm collisions, each of which has left a lasting imprint. This intricate history is written in the very chemical compositions of its stars. Every star carries within it a chemical fingerprint, an exclusive pattern of elements that was imprinted at the moment of its birth. By examining these elemental signatures, astronomers can uncover a star's ancestral history, effectively peeling back layers of time. Some stars are rich in heavy elements such as iron and calcium, which suggests they originated in dense, metal-rich regions of the galaxy, places where repeated cycles of star formation and supernova explosions enrich the surrounding matter. Conversely, other stars are composed almost entirely of the simplest elements, hydrogen and helium, born in the universe's infancy, when there were few heavier elements to incorporate. These differences in chemical makeup allow scientists to group stars into familial clusters, revealing their shared origins and tracing back the threads of ancient mergers and cosmic growth. In this way, the chemical compositions serve as a kind of natural time capsule, an intricate, luminous thread that allows us to read the history of the galaxy as if deciphering a line of ancient poetry written in the language of light. The sky above us is dotted with the faint, delicate remnants of these past cosmic events, stellar streams that are the vestiges of destroyed galaxies. Across the celestial canvas, thin ribbons of stars stretch across vast arcs in sweeping curves, subtle yet unmistakably distinct when mapped with precise instruments, remnants of former galaxies that once wandered too close to the Milky Way and were torn apart by its gravitational tides. As these smaller galaxies were pulled apart, their stars became scattered, smeared across the galaxy's halo and disk, forming intricate ghost. The shape of our galaxy appears to be a vast, elegant disk that on one side curves upward while on the opposite side dips downward. This graceful undulation creates a subtle wave-like pattern stretching across the multitude of stars, lending the galaxy a dynamic sense of motion and form. For a long time, this slight warping remained hidden from our view, largely because it is difficult to perceive with the naked eye. It was only when astronomers employed sophisticated radio telescopes to study hydrogen gas, which extends far beyond the brightness of the stars we see, that this curvature was revealed. These advanced instruments allowed scientists to map the gas clouds spanning enormous distances, well past the luminous regions of the galaxy's core, exposing a gentle but distinct distortion in the galactic disk. There is a prevailing theory among astronomers that this bend or warp could be caused by the gravitational influence of satellite galaxies orbiting nearby. Their subtle gravitational pulls tugging at the edges of the Milky Way in a slow, persistent manner. Alternatively, some scientists propose that these deviations might result from the presence of dark matter, an unseen, mysterious substance that exerts a gravitational pull from beneath the galactic plane, subtly bending the structure from below. This phenomenon resembles ripples propagating across a vast spinning sheet, illustrating that even something as grand and seemingly static as a galaxy is constantly in flux. Over immense expanses of time, galaxies do not remain fixed. Instead, they bend, flex, and reconfigure their shapes in response to forces that are invisible to us, but have profound impacts on their form. From our vantage point, or more accurately, from a cosmic distance, the Milky Way appears to be engaged in a gentle, almost hypnotic dance through the heavens. It seems to drift and sway slowly through space, its vast arms gracefully sweeping through the dark, silent void. Yet, despite this apparent serenity, the galaxy itself is a colossal, dynamic system where only an incredibly tiny fraction is visible to the naked eye. In fact, when we observe the sky under a perfectly clear and dark night, far away from the illuminations of city lights and artificial glow, we can see only a few thousand stars. That number might sound immense to us, like an ocean of shimmering points of light. But in the context of the galaxy's true scale, it is but a mere droplet in a vast cosmic sea. The Milky Way, in reality, contains over 100 billion stars, and the majority of these celestial bodies remain hidden from sight. Many stars lie behind dense clouds of cosmic dust that obscure our view. Their light is blocked by these thick curtains of interstellar material. Others are simply too faint or distant for our eyes to detect without the help of powerful telescopes. The faint, pale band that streaks across the sky on moonless nights, known as the Milky Way, is just the faintest whisper of the galaxy's true extent. It barely hints at the enormous structure that stretches far beyond our perception. This band represents only the innermost, brightest region, the core of a colossal, sprawling system of starry rivers and clouds. Despite living amidst this immense flow of light, most of it remains invisible to us, beyond the reach of human vision, illustrating just how vast and elusive the galaxy truly is. Stars within the Milky Way orbit the galactic center at varying speeds, much more chaotically than planets orbiting a single star. Unlike planets in our solar system, which follow predictable, orderly paths around the Sun, stars in this galaxy are constantly moving in different directions, with their speeds varying depending on their position. Some stars in the crowded inner regions zip along rapidly, racing towards the galactic core, while others in the outskirts drift slowly, in a more leisurely fashion. This variation in orbital velocities was crucial in understanding the galaxy's structure, leading to the discovery of spiral arms, not as solid, fixed structures, but rather as patterns similar to slow-moving traffic jams of stars and gas that sweep across space. These spiral arms are not rigid or permanent. Instead, they are density waves, regions of higher concentration that ripple through the galaxy. As these waves pass through, they compress gas and dust, triggering the formation of new stars, which ignite in bright blue-white clusters, illuminating the arms with sparkling beauty. This process creates the iconic, curling patterns of blue and white light that define the spiral structure. Our own sun, along with the entire solar system, is embedded within this swirling pattern, drifting in and out of these density waves over time, sometimes approaching the brighter, star-forming regions, other times moving into quieter, less populated zones. It's important to realize that the Milky Way is not a static clockwork mechanism. Instead, it functions more like a vast, flowing current, an immense river of stars, gas, and dust, constantly moving and changing. Within this cosmic stream, our solar system is merely a tiny boat, drifting gently along the currents beneath a canopy of countless stars. The galaxy persists because of an invisible substance, something although we cannot observe it directly with our eyes, the existence of the supermassive black hole at the very center of our galaxy is deeply evident through the extraordinary motions of the celestial bodies that orbit it. Astronomers have meticulously studied the stars in the vicinity, watching how they zoom around this unseen giant at incredible speeds, tracing intricate, invisible loops through the expanse of space. These stars, although not touching the black hole itself, are affected profoundly by its immense gravitational pull, causing them to follow precise orbital paths that reveal its presence. Occasionally, streams of gas and dust from the surrounding regions drift inward towards the event horizon, where they become heated and compressed as they spiral ever closer, emitting intense X-ray radiation. In this moment, the supermassive black hole, often referred to as Sagittarius A, remains dormant, lying in a state of relative quiet. However, long ago, it may have been an active powerhouse, shining brightly like a quasar, lighting up the core of our galaxy with a fierce radiance that outshone countless stars combined. Today, it silently governs the motions at the galaxy's core, acting as a cosmic conductor, orchestrating the slow but relentless dance of countless stars and stellar remnants, pulling them inward with its immense gravitational influence. Turning our gaze outward, the structure of the Milky Way reveals a surprisingly complex core. Instead of a smooth, uniform sphere of densely packed stars, astronomers have uncovered a striking, three-dimensional peanut-shaped central bulge. When viewed from the side, this bulge appears to bulge outward in the middle, tapering at the ends, resembling an elongated hourglass formed from luminous stars. Such a peculiar shape is believed to have originated from the galaxy's central stellar bar, a dense, elongated strip of stars that slowly rotates within the galactic center. Over millions, perhaps billions, of years, this bar has buckled and puffed outward, creating the distinctive protrusions observed today. These intergalactic structures are sculpted over vast timescales by the relentless force of gravity, the dynamic motion of countless stars, and the rhythmic dance of stellar orbits that have gradually molded the galaxy's very heart into its complex shape. Despite our classification of the galaxy as a spiral galaxy, its innermost regions are anything but simple or flat. They are alive with intricate formations and dynamic processes. This lively complexity is most vividly seen in the stellar nurseries, vast clouds of gas and dust from which new stars are born. The spiral arms of the Milky Way are not merely luminous bands of stars. Rather, these arms are woven from the birthplaces of stars, where cosmic clouds of hydrogen, dust, and molecules drift through the galaxy's sprawling disk. As these colossal clouds traverse the spiral arms, the gravitational forces within are compressed, igniting a chain reaction that leads to the formation of new stars. These regions, commonly known as stellar nurseries, are chaotic, glowing with vibrant energy, teeming with motion and life. Ultraviolet light from the nascent stars illuminates the surrounding clouds, painting the arms with brilliant shades of blue and silver, creating a radiant tapestry that traces the spiral pattern. These luminous bursts of stellar creation not only light up the galaxy's arms, but also serve as silent markers of ongoing cosmic labor, illuminating the curves of the Milky Way with a quiet, fiery brilliance. Every star, including our own sun, was born from one of these swirling, cloudy cradles long ago, contributing to the dynamic tapestry that is our galaxy. Encircling the luminous, star-filled disk of the Milky Way is a vast, diffuse halo, a spherical cloud of matter that extends well beyond the familiar spiral structure. This halo is composed of ancient stars, aged globular clusters, and enormous quantities of dark matter, the mysterious substance that exerts gravitational pull but remains invisible to our instruments. Though nearly transparent and dim, this halo appears to hold the majority of the galaxy's mass due to the gravitational effects observed in the galaxy's rotation curves. Its stars are spread thinly across enormous distances, orbiting the galactic center in long, slow arcs that rarely intersect with the more densely populated disk. The halo also preserves the remnants of ancient galactic encounters, streams and shells of stars torn apart from smaller neighboring galaxies long ago, acting as cosmic fossils. These remnants serve as a kind of ancient memory, whispering secrets of past mergers and interactions. Although it is silent and faint, the halo continually shapes the future evolution of the galaxy, influencing the distribution of mass and the motion of all its components. Within this halo reside over 150 globular clusters, ball-shaped, densely packed assemblies of stars, some of the oldest structures in the Milky Way. Each globular cluster contains hundreds of thousands of stars tightly bound together by gravity, orbiting the galactic core like moths fluttering around a distant flame. These clusters are remarkably stable, some estimated to be more than 12 billion years old. Many of their stars predate the formation of the galaxy itself. Because of their the stars within our galaxy carry with them stories etched into their very composition, and these stories reveal crucial clues about their origins. Unlike younger stars that formed after the universe had already been enriched with heavy elements through countless generations of stellar evolution, these particular stars are characterized by their remarkably low metal content, making them what astronomers refer to as metal poor. Their existence points back to a distant epoch, long before the universe had enough time to synthesize and distribute a multitude of heavier elements into space. These ancient celestial bodies essentially serve as cosmic time capsules, preserved remnants from the galaxy's earliest formative years. They hold answers to fundamental questions about how the galaxy, including our own Milky Way, came into being, what material it consumed during its infancy, and the conditions that prevailed in the primal cosmos before the complex structures we observe today had fully taken shape. These silent, luminous spheres drift through the darkness, gently oscillating above and below the vast expanse of the galactic plane. They shine softly, glowing like tiny golden beads against the vast black canvas of space, patiently enduring through billions of years. Despite the galaxy's ongoing evolution, it remains an active, growing entity. Although the Milky Way is an ancient structure, hundreds of billions of years old, its formation has not yet come to an end. The galaxy is still in the process of gathering additional material, expanding its mass, and reaching out into the surrounding universe. This accumulation takes place gradually as gas from the intergalactic medium, which is the faint, diffuse matter filling the space between galaxies, streams inward. Additionally, the galaxy continues to incorporate stars and stellar remnants from smaller satellite systems, dwarf galaxies, whose mutual gravitational pull causes them to be captured and absorbed. Streams of dark matter, which form a halo around the galaxy, also feed its growth by adding unseen mass. In essence, the galaxy does not grow as a living organism might, with sudden developments or bursts of rapid change. Rather, it increases in size and complexity like a vast gravitational structure, deepening its tendrils of mass over cosmic time. This growth manifests in two primary ways. Sometimes it occurs quietly through the gradual infill of diffuse clouds of gas and stars, merging little by little into the overall fabric of the galaxy. Other times, it involves more violent episodes, such as the tearing apart of dwarf galaxies, whose stars become dispersed across the galactic halo and beyond, creating a chaotic but spectacular process of assembly. The galaxy we inhabit today is vastly different from the one observed by the creatures that roamed the Earth millions of years ago. The dinosaurs, for example, would have seen simply a different universe, devoid of the intricate spiral arms and vast stellar populations we know now. Moreover, the galaxy's future may hold even more remarkable transformations. As generations pass and the universe continues to evolve, what our distant descendants perceive as their galaxy could be considerably larger and more complex, stitched together from the remnants of hundreds or even thousands of smaller worlds that have long since been absorbed into the larger structure. Among the dynamic and sometimes startling phenomena within the galaxy are rogue stars, stars that are hurled from the core at extraordinary velocities, far beyond the usual gentle drift of most stars. Typically, stars move through the galaxy in a calm, graceful fashion, orbiting the galactic center with little fuss. Yet, on rare occasions, some stars are cast outward at such astonishing speeds that they escape the gravitational grip of the Milky Way altogether. These are known as hypervelocity stars, remarkable objects traveling at velocities so high that they can outrun the galaxy's gravitational pull, leaving an expanding trail into the blackness of intergalactic space. Many of these hypervelocity stars are the remnants of binary star systems that were disrupted by the supermassive black hole lurking at the galaxy's core. Here is how it occurs. One star in such a binary system is pulled inward by the intense gravity of the black hole and disappears from view, perhaps consumed by the black hole itself, while its companion is flung outward at breathtaking speeds, exceeding 1,000,000 kilometers per hour. This violent ejection creates a star that travels alone through the dark, far above and below the dense plane of the galaxy, resembling a brightly glowing comet with no return trail. These stars serve as poignant reminders that even in a universe dominated by gravity, moments of intense, disruptive force can occur, violently expelling stars into the vast, empty intergalactic void. The pace of star formation within the Milky Way has been slowing over cosmic time. In its earliest days, the galaxy was a bustling environment, bursting with the birth of new stars from dense, collapsing clouds of gas, stellar nurseries teeming with activity. During that bustling era, the galaxy's star-forming rate was significantly higher, leading to the creation of countless stars, each contributing to the gradual buildup of the galaxy's stellar population. However, in more recent epochs, after billions of years, the rate of new star formation has diminished considerably. While gas remains available, a galactic year, an unimaginably vast span of time, stretches approximately from 225 million to 250 million Earth years. This measure of cosmic duration reflects the time it takes for our Sun, along with its solar system, to complete a single full orbit around the central core of the Milky Way galaxy. As the Sun embarks on this leisurely circular journey, it moves through a universe that is both magnificent and seemingly infinite in scale, covering an expansive arc that outstrips any familiar calendar or human concept of time. This enormous cycle of motion, known as a galactic year, dwarfs the timescales we normally use to chronicle earthly events and reminds us of just how ancient and slowly changing the universe truly is. Throughout the course of one such orbit around the galaxy's core, the planet continents on Earth drift subtly across the surface. Species of living beings evolve, flourish, and then fade into history, and entire epochs emerge and vanish. It is believed that we are presently situated about halfway along one of these colossal trajectories, orbiting through the galaxy's grand expanse, a journey that has been ongoing for hundreds of millions of years. Looking back in time to the last period when our solar system occupied this specific sector of the galaxy's sprawling path, we find that the land masses of our planet resembled a supercontinent called Pangaea, which had just begun to fragment into smaller continents. Interestingly, at that remote point in cosmic history, the age of dinosaurs had not yet dawned. The Earth was still in the early stages of its evolutionary saga. The concept of a galactic year serves as the slow, rhythmic heartbeat of cosmic time, recording the silent motion of galaxies through the universe. Interestingly, Our Sun has completed less than 25 complete orbits around the Milky Way's core during its entire lifetime of approximately 4.6 billion years. This means that, despite the Sun's astonishing velocity, moving at nearly 830,000 kilometers per hour, it has only circled the galaxy about 20 times in total. This fact underscores just how vast the galaxy is and how lengthy each of its orbits must be. Each full circuit takes hundreds of millions of years to complete, making our Sun a relatively young traveler within the cosmic city of stars. Compared to the galaxy's long history, our solar system is a newcomer, still settling into its place within the majestic swirl of stellar motions. We often conceive of stars as ancient, unchanging fixtures, immutable points of light that have existed forever. But in reality, our solar system is still in its infancy on a galactic scale, just one of countless celestial systems that have been wandering through the galaxy's vast arms for billions of years. It is important to understand that while we are moving with the galaxy's rotation, we remain in the early chapters of a story that has been unfolding for a truly incomprehensible span of time. Interestingly, the motion of the Milky Way galactic disk presents a fascinating challenge to classical physics. According to Sir Isaac Newton's well-established laws of gravity and motion, one would expect that stars located farther from the galactic center should orbit more slowly, much like outer planets trail behind their inner counterparts when revolving around the Sun. However, observational evidence contradicts this expectation. In the outer regions of the galaxy, stars seem to rotate almost as rapidly as those nearer to the core, defying Newtonian predictions. This perplexing behavior has led astronomers to propose the existence of an invisible, unseen component called dark matter, a mysterious form of mass that envelops the galaxy in an enormous halo. Without dark matter, the gravitational forces calculated from visible matter alone would be insufficient to keep the galaxy together at such high rotational speeds. But with dark matter, the galaxy's structure remains stable, its rotation functioning as if it were a solid wheel turning smoothly, although the true nature of what holds it in place remains one of the universe's greatest enigmas. Within the sprawling arms of the Milky Way, there exist enormous clouds of cold, dense gas, massive, dark, and turbulent regions known as molecular clouds. These are the raw nurseries where stars are born. Spanning hundreds of light years across, these clouds are primarily composed of hydrogen molecules, along with traces of dust and other elements. Their cold interiors contain a dense concentration of gas, held together by gravity, which begins to clump and collapse under its own weight. Over time, these clumps gather and compress further, eventually igniting nuclear fusion to form new stars and planets. Some of these molecular clouds are so immense and opaque that they block out the light from distant stars, appearing as dark patches against the backdrop of countless shining suns. These regions are the galaxy's silent wombs, the hidden places where the future of stars and planetary systems quietly begins, cloaked in shadow and chilly gas. Supernovae, catastrophic explosions marking the death of massive stars, serve as cosmic storms that ripple through and stir the galaxy's fabric. When powerful, luminous stars exhaust. Within the vast, ever-expanding expanse of our galaxy, countless elements of extraordinary weight and significance are woven into the fabric of space. These are heavy elements, like iron and gold, forged deep within the core of dying stars during their explosive end stages. When a star exhausts its nuclear fuel and reaches the brink of its existence, it often erupts in a spectacular explosion known as a supernova. This cosmic event acts in many ways like a tumultuous storm within the galactic ecosystem, stirring up the surrounding space, providing essential nutrients, and fundamentally reshaping the environment around it. As these supernovae erupt, they do not merely destroy, but also serve as powerful agents of renewal. They scatter their enriched guts, heavy elements, throughout the galaxy, acting as catalysts for future generations of stars and planets. In this sense, supernovae embody moments of chaos, destructive yet radiant, and are crucial to the ongoing life cycle of the cosmos. Meanwhile, vast regions within the galaxy are cloaked in dense clouds of cosmic dust, masking areas where new stars are quietly forming. Our galaxy, the Milky Way, shines brightly across the universe, yet most of its brilliance remains hidden from our direct sight. Interstellar dust, composed of tiny grains made from carbon, silicate minerals, and ice, pervades the galaxy in intricate networks of clouds and ethereal filaments. This dust acts like a cosmic veil, obscuring many regions of space from view when observed in visible light. The dense dust clouds often conceal entire star-forming nurseries, making it appear as if these regions are empty or dark. But behind this shadowy curtain, a remarkable process unfolds. Infrared telescopes, capable of seeing through these dust clouds, have allowed astronomers to peer into these hidden nurseries, revealing sparkling regions where new stars are being born in brilliant clusters. What appears to be darkness or emptiness to the naked eye is, in reality, a cradle of stellar creation. The dust, despite hiding the process, plays a vital role in it. It absorbs and redistributes energy, helping the surrounding gas cool and condense, and shields the fragile environments where stars take shape. In essence, what may seem like nothingness is often the birthplace of something extraordinarily luminous and alive. Scattered throughout the galaxy, there are also enormous clouds of gas that show no signs of imminent star formation. These clouds, rich in molecular hydrogen, the raw material for stars, may look dormant, but they hold great potential for transformation. Not every gas cloud is destined to give birth to a star. Many are either too dispersed or stabilized by magnetic forces and internal turbulence, preventing them from collapsing under their own gravity. These silent cold clouds drift slowly through the galaxy, untouched perhaps for millions of years, awaiting a catalyst that might set them into motion. They are like sleeping giants, containing the building blocks for future stars, waiting for a faint external nudge, such as a nearby supernova shockwave or interactions with other clouds, to ignite their process of collapse. Until then, they are simply reservoirs of molecular hydrogen, floating in space as quiet possibilities for cosmic rebirth. The galaxy continually recycles its matter across countless generations of celestial objects. Stars, once born and shining brightly for millions or billions of years, are not forever. They burn, evolve, and eventually perish. When they reach the end of their lives, they return their material, gas, dust, and heavier elements, back into the interstellar medium, enriching it anew. Supernova explosions cast heavy metals into space, spreading elements like iron, nickel, and other metals far and wide. Red giant stars gently shed their outer layers, creating luminous planetary nebulae, delicate shells of glowing gas drifting outward. Over time, These enriched materials mingle with the surrounding cold gas, cooling and condensing once again to form new stars, planets, and, ultimately, the building blocks of life itself. Every atom in your body has undergone this cosmic journey. It was born in the heart of an ancient star, expelled into space through violent or gentle means, and later incorporated into a new celestial body. The Milky Way, far from being a fixed and unchanging structure, functions as a magnificent engine of renewal, continually breathing in, transforming, and exhaling matter and energy. It is a dynamic, vibrant place where destruction and creation are two sides of the same coin, where the cycle of birth, death, and rebirth operates seamlessly and without pause. Stars also serve as celestial clues, illuminating the universe's earliest epochs and revealing the history of cosmic chemical enrichment. In the realm of astronomy, the term metals does not refer solely to materials like iron or gold. Instead, it encompasses all elements heavier than helium. The earliest stars that formed in the universe contained almost no of these heavier elements because they existed before any previous generations of stars could forge and scatter these materials across space. As a result, ancient stars, particularly those residing in the galactic halo, are often extremely metal poor and faint, standing as relic. They are essentially celestial fossils composed solely of light, remnants of ancient cosmic processes that shine through the vastness of space. Some stars, over their long cosmic journeys, tend to wander far from the regions where they originally formed. It's important to recognize that the specific birthplace of a star does not necessarily predestine its ultimate destiny within the galaxy. Throughout billions of years, numerous stars gradually drift away from their natal clouds, propelled by complex gravitational interactions, the subtle influence of orbital resonances, or the gentle, persistent pull of spiral arms that wind around the galaxy's core. In some cases, stars are abruptly ejected at incredibly high velocities, so fast that they are propelled across the galactic disk or launched into the halo, the faint, spherical region surrounding the main body of the galaxy. Other stars, however, move more gradually, slowly shifting their orbits either inward or outward as they spiral through the galactic plane. Even our own sun is not located exactly where it was born, having migrated over billions of years from its original position. Tracing the intricate paths that stars take across the galaxy reveals a picture of the Milky Way that defies any idea of stillness. It is a dynamic, living entity, continually in motion, exchanging material, and experiencing quiet displacements. For many of these stars, the place that feels like home may only be temporary. The so-called habitable zone within our galaxy might stretch across tens of thousands of light years. Just as Earth orbits the Sun within what we term the Goldilocks zone, neither too hot nor too cold for sustaining life, the Milky Way itself could host its own galactic habitable zone. This particular region is believed to lie between the perilous, radiation-filled inner core, which is rife with gravitational chaos, and the outermost edges where matter is so sparse that forming planets becomes increasingly difficult. Somewhere in the middle, there exists a broad band where conditions are relatively stable. Star density is moderate, and essential elements such as carbon, oxygen, and iron are plentiful. Our home planet Earth resides within this relatively hospitable zone, one quiet orbit amid the vast swirling arms of the galaxy, in a region where conditions could favor life. Within this zone, Stars and planets seem to enjoy a kind of cosmic safety net, offering a better chance for life to develop and persist. The galaxy's iconic spiral arms are often perceived as fixed, immutable structures, grand sweeping lines etched into the galactic disk. However, this is a misconception. The spiral arms are not constellations of fixed stars, but rather pattern formations, density waves that ripple through the galaxy's disk, propagating slowly and gracefully. These waves periodically compress clouds of gas and dust as they move through the galaxy, often triggering new waves of star formation in their wake. Stars drift into these spiral arms, burn brightly for a time, and then drift out again, contributing to the ongoing cycle of galactic renewal. The spiral pattern itself travels at a different speed from the stars, much like a traffic jam moving through a busy highway, an emergent, shifting pattern rather than a rigid structure. Observed from a distance, the galaxy appears organized and majestic. But from within, astronomers see a universe in perpetual flux, a pattern sustained by gravity and the relentless march of time, always flowing, never static. The Milky Way is also alive with an invisible hum of cosmic radiation, a mysterious and complex environment that extends well beyond the visible light we see with our eyes. Beyond what the human eye can capture, the galaxy radiates with various forms of energetic emissions. Cosmic rays, high-energy particles born from supernova explosions and distant galaxies, stream through space at nearly the speed of light, passing through every object, including your own body, countless times each second. X-rays and gamma rays shimmer faintly from cataclysmic events such as dying stars and black holes, revealing violent and energetic processes hidden in the galaxy's depths. Radio waves drift gently from gaseous clouds, pulsars, and the cold hydrogen gas that permeates the galaxy, creating a faint, pervasive background hum. These invisible signals and energies reveal much about the hidden workings of the Milky Way, its violent past, magnetic fields, and ancient fires still flickering in its core. When we gaze up into the night, what we see is only a narrow slice of this broader spectrum. Beneath the familiar glow of the stars, the galaxy hums in many colors and frequencies, forming a complex hidden symphony beneath the darkness. Above and below the central region of the galaxy, extending tens of thousands of light years into the halo, there exist gigantic, ghostly bubbles of high-energy radiation. These structures, known as the Fermi bubbles, discovered only in recent years, are enormous, mysterious regions of glowing, energetic light, stretching far above and below the galactic core, like spectral loaves cast into the cosmic abyss. They represent some of the most powerful and enigmatic phenomena within the galaxy, remnants of ancient energetic processes that continue to. They emit a faint but persistent glow in gamma rays, forming two colossal, luminous structures that stretch outward from the very core of the Milky Way. These formations resemble enormous, symmetrical balloons of high-energy radiation, protruding from the galaxy's center in opposite directions, creating a mirror image of sorts. Despite their imposing appearance and vast size, scientists remain somewhat in the dark about their true origins. While there are several hypotheses, one prevailing idea suggests that these gamma ray features are the remnants of a powerful, ancient outburst emitted by the galaxy's central supermassive black hole long ago. Alternatively, they could be the lingering traces of intense star formation activity that once surged through the galaxy's core, leaving behind these radiant signatures as clues to its tumultuous past. Regardless of their specific origin, these colossal structures drift silently and unobtrusively through the vastness of space, their faint glow invisible to human eyes, but detectable through sensitive instruments. They serve as silent witnesses to the galaxy's history, arching mysteries that remind us of a history we can't fully observe or understand. These glowing formations are echoes of violent events and energetic processes, radiant scars of the galaxy's past, floating far above the familiar star fields we see in the night sky. Living within this grand galaxy means inhabiting only a tiny part of a much larger story. Unlike some of the more prominent spiral arms that stretch out across billions of miles, our solar system is positioned in a relatively quiet, lesser-known region called the Orion Spur. This is a modest branch, a relatively calm corridor of stars nestled between two much larger and more active arms, namely the Sagittarius arm on one side and the Perseus arm on the other. This sector of the galaxy isn't densely packed with stars, nor is it especially turbulent, but perhaps that subdued environment is exactly what allowed life to emerge and flourish here. In the peaceful zones between the major spiral lanes, violent supernovae are less frequent, and radiation storms, powerful bursts of energetic particles, are comparatively rarer occurrences. This tranquil setting may have granted Earth, and subsequently life on our planet, enough time and stability to develop complexity and diversity. From our vantage point on the outskirts of the galaxy, the Milky Way appears vibrant and radiant, an impressive spectacle of stars, dust, and glowing clouds. Yet, within our quieter neighborhood, the calm and stability seem almost like a sanctuary, offering the perfect conditions for evolution to proceed without constant upheaval. At the heart of our galaxy lies an intriguing structure, a bar-shaped core composed of densely packed stars stretching across the middle in a thick, elongated formation. When astronomers observe this region in infrared light, which penetrates the dense dust obscuring many cosmic features, they don't see a perfect circle, but instead discern a prominent, glowing bar of stars crossing through the center. This structure acts like a luminous bridge, linking various parts of the galaxy's inner regions. The bar rotates slowly, exerting a gravitational influence that actively shapes the galaxy's inner spiral arms and directs the movement of gas, dust, and stars nearby. Such bars are commonly observed in spiral galaxies, but their presence signifies much more than a mere shape. They are dynamic engines, massive, rotating structures that help regulate the life cycle of stars, funnel material inward toward the galaxy's core, and feed the supermassive black hole lurking in the center. Over time, these bars stabilize and evolve, stirring up the surrounding material and igniting the formation of new stars in the process. They also play a vital role in driving the galaxy's internal evolution, acting as sculptors that shape both its appearance and its future. Far from being a static feature, this bar functions as a busy, rotating engine, an active component that continuously influences the galaxy from within. Our Milky Way doesn't exist in isolation, but is part of a larger cosmic structure known as the local group. This vast assembly includes more than 50 individual galaxies, all drifting through space together as a cosmic family. Among these, the two most massive members are our home galaxy, the Milky Way itself, and the neighboring Andromeda galaxy. Each of these giants is surrounded by an entourage of smaller satellite galaxies, ranging from faint dwarfs to more substantial elliptical galaxies, many of which are composed primarily of dark matter, a mysterious, invisible substance that exerts a gravitational pull. The scope of this local group extends for more than 10 million light-years, yet despite such staggering distances, the galaxies are bound together not by proximity alone, but by the invisible but powerful force of gravity. This gravitational connection causes the member galaxies to move in a coordinated fashion, creating a complex, slow-motion ballet across the cosmos. Many of these smaller galaxies orbit their larger neighbors like moons circling planets, gradually falling inward, occasionally dissolving into streams of stars, or drifting peacefully in their paths. Despite the enormous spaces that separate them, the members of this cosmic family are interconnected through shared motion and mutual gravitational attraction, a web of interactions that keeps them linked in an intricate gravitational dance, each galaxy in the group aware. Over countless eras, the vast assembly of stars, gas, dust, and dark matter that we call a galaxy does not remain in a fixed, unchanging state. Instead, it often undergoes gradual but profound transformations. Over extended periods, these colossal cosmic entities may become more tightly packed, with individual groups of stars and interstellar material drawing closer together as if gravitating toward a common center of gravity's inevitable pull. Sometimes, galaxies may drift into one another and merge, blending their distinct features into a new, singular structure. Other times, they gradually diminish in brightness and prominence, but are absorbed into larger systems, fading away like distant flames swallowed by the darkness. Galaxies are not static arrangements frozen in time, but are dynamic, ever-shifting collections, akin to gentle islands of light and matter drifting through the cosmic ocean, gently drawn closer over aeons by the unyielding but unseen influence of gravity. This ceaseless ebb and flow give the universe its rich tapestry of forms and structures, each one an expression of the persistent dance of matter shaped by the passage of time and cosmic forces. Within this grand environment, a galaxy's disk exhibits a fascinating complexity. Although from afar, it appears as a flat, uniform band of light stretching across the sky, the reality closer to home reveals a layered and textured inner world. The disk is composed of two distinct regions, a dense, thin component and a more spread out, thicker layer. Our galaxy, the Milky Way, appears as a broad, relatively flat disk when viewed from a distance, a glittering band of stars arching through the night sky. Yet, upon closer inspection, this seemingly simple structure proves to be constructed of multiple layers, each with its unique characteristics. The thin disk is where most of our familiar stars reside, a broad, densely packed plain filled with youthful stars, open star clusters, and clouds of gas actively collapsing to form new stars. This region is where the ongoing birth of stars takes place, creating a vibrant, ever-changing stellar nursery. Immediately above and below this bright, thin layer exists the thick disk, often more diffuse, containing older stars that have drifted into more elongated and inclined orbits. These stars tend to be older, with fewer heavy elements, meaning they were formed earlier in the galaxy's history when fewer heavy substances were available in the universe. Their paths around the galactic center are more tilted, more elliptical, hinting at a different origin story or subsequent disturbance, perhaps stemming from ancient cosmic collisions or turbulent phases of galactic growth. The entire disk is not a monotonous structure, but a complex, layered, textured environment shaped over cosmic time, like sediments quietly settling in the deep layers of an ocean floor, gradually accumulating and revealing the history of the galaxy through its subtle strata. Interwoven through this intricate structure is the galaxy's magnetic field, a force invisible to the eye yet profoundly influential. Extending across the plane of the galaxy, rising into the halo, and threading through the interstellar medium. This magnetic tapestry is like a vast cosmic web. Though it is measurably weak compared to magnetic fields that can be generated artificially here on Earth, its effects are far-reaching when considered across the enormous scales of the galaxy. It guides the movement of charged particles, influences the flow of gas and dust, and impacts processes such as star formation and cosmic ray propagation. This magnetic field aligns along the spiral arms, forming graceful arcs that ripple above and below the galactic plane, twisting into loops and helixes that often seem to defy simple explanation. Studying it requires sophisticated techniques, radio telescopes, and detailed analysis, yet its omnipresence becomes unmistakably evident. The Milky Way, far from a mere luminous band, breathes with an unseen magnetism, a subtle, rhythmic pulse coursing through its fundamental components. It's a silent, omnipresent force that shapes the very dynamics of the galaxy, influencing everything from the flow of interstellar matter to the trajectories of high-energy particles traversing space. The space between the stars, the interstellar medium, is not mere emptiness, but a complex, living web of matter that weaves through the galaxy like a delicate fog. This region consists of a tenuous mixture of gas, dust, and plasma, so sparse that to the naked eye it is practically invisible. However, with the help of radio and infrared telescopes, astronomers unveil its true nature, a stunning realm filled with intricate structures, including filaments stretching across light years, bubble-shaped cavities carved out by energetic processes, shock waves rippling through the gas, and cold, dense clouds where stellar nurseries ignite. These cold clouds are the cradles of star birth, their dense regions collapsing under gravity's relentless pull, giving rise to new generations of stars. Occasionally, violent supernova explosions carve vast cavities and create shock fronts, sending waves rippling outward into the surrounding medium. Stellar winds, streams of charged particles expelled from stars, sculpt the interstellar environment into elaborate shapes, sometimes spanning multiple light years. Contrary to being empty voids, these regions, the vast galaxy we inhabit, is far from perfectly symmetrical or uniform, even though many visual representations tend to depict it as a perfectly organized, elegant spiral. In reality, the structure of the Milky Way is more complex and asymmetrical. One of the most noticeable deviations from symmetry is the noticeable thickening of one side of its sprawling disk, which hints at a turbulent history. Some of the spiral arms are more luminous, stretching out longer than others, or twisting into slightly more pronounced curves, giving the galaxy an uneven but intriguing appearance. Additionally, the outer regions of the galaxy exhibit a noticeable warp that is uneven or tilted to one side. When astronomers compare star counts across different hemispheres of the galaxy, they observe subtle differences and disparities, further emphasizing its asymmetrical nature. These irregularities are not random, but are likely the results of intricate gravitational interactions, ancient cosmic collisions, or the ongoing influence of dark matter. Such features serve as silent but powerful reminders that galaxies are not static, perfect entities. Instead, they are living entities, bearing the marks of their tumultuous pasts. Their shapes are scarred by past encounters, marked by the scars of collisions, wrinkles of cosmic time, and quirks of uneven growth. All these elements combine to give each galaxy its unique character, depth, and a sense of organic evolution over billions of years. In the outskirts of our galaxy, in the sparse regions far above the dense galactic plane, astronomers have made a remarkable discovery. What may be the oldest star known to exist in the universe? Suspended high in the halo that surrounds the Milky Way, this ancient star drifts quietly among the stars, almost untouched by the passage of time. What makes this star especially intriguing is its composition, an almost complete absence of heavy elements such as carbon, oxygen, or iron. This paucity of metals is a vital clue, indicating that the star was born very early in the universe's history, shortly after the Big Bang, when the cosmos was filled primarily with hydrogen and helium. It is believed to have formed more than 13 billion years ago, long before the Milky Way itself was fully assembled from merging gas clouds and countless smaller structures. Today, this star glows softly with a gentle red hue, a silent witness to an age when the universe was young and its first generations of stars had yet to forge heavier elements. Although it now exists as a faint, low-mass star, it holds an extraordinary significance. It acts as a living historical record, a tangible relic from the universe's earliest dawn, proof that the cosmos is ancient and filled with remnants of its primordial origins. When we examine the dynamics of our galaxy's rotation, a fascinating pattern emerges. The core, or the very center of the Milky Way, spins at a faster rate than the regions farther out in the galactic disk. In the innermost zones, stars experience a much stronger gravitational pull due to the high density of stars, dust, and the central supermassive black hole, known as Sagittarius A-Bon. This concentration of mass causes stars orbiting close to the galactic core to race around on tight, rapid paths, completing their revolutions in just a few million years. Conversely, stars located in the outer regions, where the influence of the central mass diminishes, orbit the galactic center more leisurely, taking hundreds of millions of years to complete a single orbit. This disparity in rotational speeds results in a complex, twisting motion within the galaxy, with the inner regions whirling swiftly while the outskirts move more slowly. Such differential rotation prevents the galaxy from rotating as a rigid, solid body and instead creates a dynamic, ever-changing structure. The inner parts spin rapidly, dragging the central regions forward, while the outer parts lag behind, producing a lopsided, swirling motion reminiscent of a vast, spinning wheel with one edge trailing behind. The spiral arms of the Milky Way are not fixed structures made up of permanent streams of stars. Instead, they resemble the pattern of ripples, or waves, that move through the galaxy's disk. These arms are created by what scientists call density waves, areas of higher than average material density that propagate through the galaxy in a manner similar to ripples spreading across the surface of a pond. As clouds of gas and dust flow through these density waves, they experience compression, which often triggers the process of star formation. The compressed gas becomes dense enough to ignite nuclear fusion, giving birth to bright, young stars that light up these spiral arms. Over time, these newly formed stars drift away from the density wave pattern, while new generations of stars continue to form behind them. This ongoing cycle creates the illusion of a structured pattern that appears relatively stable from afar, but is, in reality, a constantly moving, dynamic process, much like traffic waves moving along a busy highway, or ripples spreading across a pond's surface. From a great distance, the arms seem motionless, but from within the galaxy, they are a constantly shifting dance of matter, gravity, and time, shaping the very essence of our cosmic neighborhood. As vast clouds of gas and dust drift inward toward the center of a developing galaxy, they undergo a fascinating transformation. As these clouds move closer to the core, they are compressed by gravitational forces, which causes them to heat up significantly. The spinning motion of the gas cloud causes it to flatten and spread out into a rotating, pancake-like structure, known as a protoplanetary or protostar cloud. Within this swirling mass, the density of matter increases over time, and the temperature rises accordingly. Eventually, this process leads to the formation of a dense core, essentially a protostar, that resides at the heart of the cloud. As the pressure and temperature continue to escalate within this nascent core, it reaches a crucial threshold that triggers nuclear fusion, the process where atomic nuclei combine to release energy. Once fusion begins, a radiant, luminous new star emerges from the cosmic cradle. Paradoxically, some of the most brilliant points of light in the universe originate in the coldest, darkest regions, shadows from which radiant lights are gently born through the quiet but relentless tug of gravity. This celestial force acts as an unseen sculptor, shaping the birth of stars from seemingly lifeless clouds of gas. Stars do not always exist in solitude. Rather, many begin life within densely packed clusters that share a common origin. These stellar nurseries, formed from the gravitational collapse of the same giant gas cloud, produce tight-knit groups of stars held together by mutual gravitational attraction. For millions, sometimes billions, of years, these clusters drift through the galaxy as cohesive entities, their members orbiting in unison, bound by the chain of gravity. Yet, this unity is not forever. Over time, the bonds that hold these stellar families weaken and gradually break apart. Various influences, such as the tidal forces exerted by the galaxy's overall mass, close encounters with other stars, and the intricate internal dynamics of the clusters themselves, work tirelessly to disperse these groups. Stars are pulled away from their original clusters one by one, ultimately causing the once bright, dense gathering to fade away into the broader field of stars that fill the galaxy. In this way, stellar clusters slowly dissolve into the galaxy's vast, sprawling starfield, their individual members becoming lone travelers amid billions of other stars. Long ago, our sun was just another star among a cluster, born from the same cosmic cloud as many of its siblings. Over aeons, these sibling stars have drifted apart, with some fading into darkness or becoming lost in the vast distances that separate them. Today, the galaxy harbors incredibly old stars as well, some of the most primitive and metal-poor stars known to science. Among the rarest and most correspondingly valuable objects in the Milky Way are these hypermetal-poor stars, celestial bodies whose atmospheres contain almost negligible amounts of elements heavier than helium. In fact, some of these ancient stars have less than 110,000th the amount of iron present in our Sun. These stars are thought to be among the earliest to form after the universe's first supernova explosions. They carry only faint, almost trace-like signatures of chemical enrichment from a universe still in the nascent stages of its development. These stars, astonishingly old and remarkably pristine, are scattered across the galaxy's halo, an extended spherical region surrounding the galactic disk. To the skilled eye, they resemble distant, flickering lanterns illuminating a period long before the birth of our solar system, a faint yet fundamental remnant of the universe's earliest moments. Each of these stars is akin to a relic, a glowing, gravitationally bound testament from an epoch that time has nearly obscured, offering vital clues to the universe's infancy. Throughout the galaxy, planetary systems form naturally as integral components of star formation, emphasizing that planets are far from uncommon. Instead, they are a fundamental consequence of how stars come into existence. When a new star ignites, it does so surrounded by a swirling, rotating disk composed of the leftover gas, dust, and debris from the star's formation process. Within this circumstellar disk, microscopic particles collide and stick together, gradually gathering mass, growing larger, and beginning to take shape into planetary bodies. Over cosmic timescales, these particles coalesce into planets, moons, and other smaller bodies, forming intricate systems that orbit their parent stars. Across the sprawling expanse of the Milky Way, a multitude of such planetary systems exist, each with its own unique architecture. Some are expansive, hosting massive gas giants and icy moons, with orbits that span wide regions around their stars. Others are more compact, closely hugging their parental stars, with rocky planets resembling Earth or Mercury, orbiting in tight circular paths around dimmer stars. The diversity is astonishing. Some planetary systems bear striking similarities to our own, while others are entirely unlike anything we have yet imagined, defying our expectations and challenging our understanding of planetary formation. The galaxy is not just a stellar city filled with countless stars, but also a vast collection of interconnected systems, solar families, each with its own balance. As our sun gracefully journeys through the vast expanse of the Milky Way galaxy, it does not follow a perfectly flat or static path akin to a straight line traced in space. Instead, it moves in a slow, gentle oscillation, reminiscent of a delicate wave undulating through the cosmic ocean. Over tens of millions of years, an incomprehensibly long span of time, the sun drifts gradually above and below the thin, flat plane that defines the galactic disk, much like a cork bobbing in a tranquil, slow-moving stream. This vertical movement, called oscillation, is driven by the gravitational tug exerted by the galaxy's enormous mass, which pulls the solar system downward and then releases it, causing it to sway gently in its orbit. Some scientists have even pondered whether this subtle bobbing might influence cyclical events on Earth, such as mass extinctions or other geological phenomena, although the current evidence remains inconclusive and subject to ongoing research. Nonetheless, this motion serves as a profound reminder that even the most seemingly steady pathways in space are, in fact, marked by gentle, rhythmic movements. The sun's orbit around the galactic center is not one of complete smoothness. Instead, it resembles a seamless sway through the universe, oscillating wistfully over millions of years. Despite the apparent steadiness of its orbit, our sun does not glide along a perfectly flat trajectory. Instead, it performs a slow, rhythmic sway in the vertical direction, a motion determined by the complex gravitational forces of the galaxy's massive constituents. Although we do not yet fully understand the nature of dark matter, a mysterious, invisible substance that permeates the universe, its presence is undeniable, exerting a significant influence on cosmic structures. Dark matter makes up the majority of the galaxy's total mass, yet it remains elusive because it neither emits nor absorbs light, rendering it invisibly silent. It moves effortlessly through ordinary matter, as though it weren't there, but its gravitational effects are unmistakably evident. This unseen material acts as a binding scaffolding, holding the galaxy together against the centrifugal forces of rotation. It accounts for the surprisingly rapid orbital velocities of stars, speeds that cannot be explained by visible matter alone, and it shapes the large-scale architecture of the cosmos itself. Without dark matter's invisible yet pervasive presence, the galaxy would lack the gravitational glue necessary to maintain its structure, and it would disperse into the cosmic void. Astronomers do not observe dark matter directly. Instead, they infer its existence by carefully studying the motions and gravitational interactions of stars and other celestial bodies. In this way, dark matter remains one of the universe's most profound mysteries, an invisible, silent framework that underpins the grand design of the cosmos. When we think about the Milky Way galaxy, our minds often picture its stunning spiral arms sweeping outward, filled with countless stars and glowing clouds of gas and dust, forming the luminous, starry plane that we see. However, this glowing disk represents only the visible surface of a far more massive structure. Most of the galaxy's true mass, its gravitational backbone, is hidden away, residing largely outside this bright, flattened disk. Encasing the luminous core and the spiral arms is a vast envelope known as the dark matter halo, an enormous, diffuse region extending far beyond the reach of the galaxy's visible stars. This halo, composed predominantly of the mysterious dark matter, provides the necessary gravitational force to hold the galaxy together, outweighing the combined mass of all the stars, gas, and dust we can detect. Though the halo appears sparsely populated with ancient, faint stars and globular clusters, dense groups of old stars, it is overwhelmingly composed of unseen matter. It serves as an invisible scaffold, enveloping the galaxy in a quiet, encompassing shroud that influences its shape, stability, and dynamic evolution. In essence, our picture of the Milky Way is incomplete if we focus solely on its luminous spiral arms. The true essence of its structure, its gravitational identity, is largely concealed within this invisible, extensive halo that enfolds the entire galaxy. The heart of our galaxy, the core region known as the galactic center, has experienced periods of intense activity over its long history. Currently, it appears tranquil from our vantage point, radiating in a subdued manner, and lacking the dramatic brightness seen in some active galactic nuclei. However, evidence suggests that in the past, this central region may have been far more energetic, flaring dramatically in a powerful display of cosmic activity. Observations of immense gamma-ray emitting structures, such as the Fermi bubbles, vast balloon-like features extending above and below the galactic plane, and traces of high-energy emissions reflected in diffuse clouds of gas hint at a turbulent past. These phenomena are believed to be the remnants of a time when the supermassive black hole residing at the galaxy's core was actively accreting matter, flaring intensely like a quasar, a luminous, high-energy beacon powered by infalling material. Quasars rank among the brightest objects in the universe, capable of outshining entire galaxies. Encounters with dwarf galaxies, and the elusive dark matter that permeates the universe can have profound effects on the structure and shape of larger galactic systems. Over billions of years, these gravitational interactions, along with the complex dance of cosmic matter, can bend, twist, and reshape a galaxy's form in ways that are often subtle yet undeniably present. As time progresses, the once clear outline of a galaxy can gradually drift and shift, akin to a cloud adrift in the sky, constantly morphing and adapting to the gravitational influences acting upon it. The galaxy we observe today, the Milky Way, is not static. It bears only a fleeting resemblance to the galaxy it was millions or billions of years ago, and it will never exactly match the form it will take in the distant future. Its true beauty, therefore, does not lie in permanence or rigidity, but in its quiet and relentless transformation, an ongoing process driven by the vast and dynamic forces of the universe. Deep within this cosmic fabric, ripples known as gravitational waves propagate outward from cataclysmic events occurring in distant corners of space. These waves are subtle, yet their existence is a testament to the violent, energetic processes that continuously unfold across the cosmos. When massive objects collide, black holes spiraling into one another, neutron stars crashing together, or entire galaxies merging, the immense energies involved send out ripples through space-time itself. These waves ripple through the universe, extending for billions of light years, carrying with them the echoes of ancient cosmic cataclysms. Although initially faint and difficult to detect, some of these waves manage to pass through our galaxy, slightly distorting the very fabric of space as they travel. The instruments capable of perceiving these faint distortions, such as the Laser Interferometer Gravitational Wave Observatory, or LIGO, and the Virgo detector, have already succeeded in capturing several of these space-time ripples. Scientists are now engaged in new, increasingly sophisticated experiments designed to detect the background hum, a constant, pervasive symphony of gravitational waves that fills the entire cosmos, providing invaluable insights into the universe's most mysterious processes. Even as you sit quietly, at this very moment, space itself is subtly shifting around you. These movements are often imperceptible to our senses, yet they reveal that the universe is in a constant state of flux. Somewhere, far beyond the reach of our eyes and instruments, the fabric of space-time is vibrating, stretching, and contracting, a silent dance of cosmic change that is happening all the time. In the vastness of the galaxy, not all stars follow simple, circular paths around the central bulge. Instead, some celestial bodies move along elongated, tilted orbits that take them high above, below, or at unusual angles relative to the main galactic plane. These stars trace long, stretched elliptical paths, their journeys tilted at odd or unexpected angles from the primary disk. Many of these stars are relics, remnants of ancient dwarf galaxies that the Milky Way once absorbed, or survivors of primordial gravitational upheavals that shaped the galaxy's early history. Their intricate, three-dimensional orbits serve as scattered clues, a cosmic map, offering a glimpse into the chaotic, tumultuous past of our galaxy. By carefully tracking their motions, astronomers work tirelessly to reconstruct the invisible architecture of the Milky Way's mass distribution and to piece together its dynamic history. These stars act as messengers from long disrupted systems, tilted and stretched by gravitational forces, yet still held tightly within the galaxy's vast gravitational embrace, silently narrating tales of cosmic upheavals. The Milky Way itself is permeated with millions of neutrinos, a type of ghostly, nearly massless particle that traverse the galaxy and pass through everything, including your body, every second of every day. In fact, trillions of neutrinos stream through you right now, streaming in from countless stars and cosmic events across the universe. These particles are born in a variety of extremely energetic processes: nuclear reactions within the Sun, the explosive death throes of supernovae, and high-energy cosmic rays colliding with atoms in space. The galaxy is immersed in this seething sea of neutrinos, which carry invaluable information from places deep within stars, from collapsing stellar cores, and from the universe's most energetic phenomena. Because neutrinos are so incredibly light and unreactive, they rarely interact with matter, slipping through most objects unimpeded, leaving no trace of their passage. To detect these elusive particles, scientists have constructed specialized observatories, buried deep underground or hidden beneath thick ice sheets, designed to catch rare, fleeting flashes of light produced when neutrinos occasionally collide with atoms. These faint signals are invaluable, serving as direct messengers from regions of space that are otherwise shrouded in darkness. They carry information from the heart of stellar explosions, from the collapsing cores of massive stars, and from the unseen energy that powers the cosmos. In essence, neutrinos are the whispers of cosmic fire, providing insights into the universe's most intense and concealed processes. The space between. From a distance, the celestial scene might appear tranquil, a serene tapestry of glittering stars shimmering with a gentle, steady glow that resembles calm, distant starlight. Yet, upon closer inspection, this impression dissolves into a more complex living fabric, a dynamic and intricate mosaic that ripples with energy and movement. This cosmic material is constantly shaped and reshaped by elusive forces, like invisible winds flowing through an ancient, vast ocean of space, and by energies that have existed since the dawn of the universe itself. The halo surrounding our galaxy, for instance, is not simply a uniform, empty shell. Instead, it may contain rogue planets, lonely worlds wandering independently through the galactic expanse, unbound by the gravitational tether of a star. These planets do not always form in conjunction with a parent star. Some emerge through dramatic, violent events, only to be later expelled from their original systems into the cold darkness. Others may have existed in the galaxy's infancy, never having been associated with a star at all. Such rogue planets drift silently and endlessly through the galactic void, dark, frozen, and isolated. Detecting these solitary worlds remains a challenge due to their lack of illumination. Yet scientific studies suggest that billions of them could be spread across the Milky Way galaxy. Many reside in the galaxy's outer halo, where the density of stars significantly diminishes, making the regions even more difficult to observe. Without a stellar glow or warmth from nuclear fusion, these planets are nearly invisible, floating unseen through the vast reaches of space. They are kept warm only by residual internal heat, a faint remnant of their formation, making them isolated wanderers, orphans of the galaxy, following long solitary paths through the darkness that separates the brighter stellar neighborhoods. Meanwhile, the flow of cosmic dust does not passively drift through space without influence. Instead, magnetic fields thread through the galaxy, shaping the movement of tiny particles of interstellar dust, minute grains composed mainly of carbon and silicates that dance and swirl with a purpose. These tiny grains are not only subject to gravity, but also respond actively to the magnetic environment, which acts as an invisible current guiding their trajectories. As these magnetic fields weave through the galaxy, they influence how dust and gas align, creating complex patterns of motion and structure. In some regions, dust particles spin rapidly, emitting faint microwave radiation that can be detected by sensitive instruments, revealing their rapid rotations. In other areas, these grains align with magnetic field lines, polarizing passing light from distant stars, thus modifying the way we perceive the universe. By studying these effects, how dust interacts with magnetic fields, how it spins or aligns, astronomers are able to map the intricate architecture of galactic magnetic fields. This knowledge is crucial not only for understanding the behavior of interstellar dust, but also for parsing out the true signals from the cosmic microwave background, the afterglow of the Big Bang. By filtering out the influence of magnetic influences that can obscure the universe's earliest light. Interstellar dust is far from inert or passive. It is a lively participant in the galaxy's ongoing story, moving and dancing to the rhythm of magnetic forces. These movements often hide subtle, intricate patterns within the darkness of space, silent, yet persistent. In addition to the silent dancers of dust and rogue planets, the galaxy's history is enriched by spectacular cosmic events. One such example occurs when neutron stars, ultra-dense remnants of exploded stars, spiral inward and collide in a cataclysmic merger known as a kilonova. This brief but extraordinarily luminous explosion is among the universe's most violent phenomena, releasing vast energy and forging heavy elements, substances that we find in the Earth's crust and in precious metals like gold and platinum, as well as in radioactive elements such as uranium. During these violent collisions, enormous quantities of these elements are cast outward, dispersing into space and mingling with surrounding gas clouds. Over time, this enriched material becomes part of new stars and planetary systems. Some stars within the Milky Way bear chemical signatures that clearly indicate their formation from the debris of such ancient rare events. These stars carry within them the fingerprints of cosmic explosions, hosting an abundance of heavy elements that could only have been produced in the intense environments created during neutron star mergers. Such stars are not merely luminous spheres of plasma. They serve as living records, testaments to cataclysmic episodes in stellar alchemy, capturing the remnants of cosmic wreckage and alchemical processes that have shaped the galaxy over eons. The very core of the Milky Way hints at a deeper, hidden structure, possibly a complex nested system of bars, each one influencing the galaxy's dynamics in subtle yet profound ways. At the center, astronomers observe a prominent elongated structure of light, called a bar, extending across the central bulge of the galaxy. But recent evidence suggests there might be more to this picture. A smaller, secondary bar nested within the larger one, tilted at a different angle and rotating independently. This inner bars, in the vast stretch of the universe, immense and intricate networks of matter known as the cosmic web stretch across the cosmos, their threads woven through the darkness, like gigantic and delicate tendrils that connect galaxies to one another. Flowing along these enormous filaments are long, tenuous streams of gas, whose journey takes place over staggering distances and spans countless millions of years. These slender, almost whisper-like streams are fundamental to the ongoing life cycle of galaxies. They serve as the vital source of raw material needed to forge new stars, effectively replenishing the galaxy's supply that gradually diminishes as stars burn bright and fade away. Some of this inflowing matter arrives gently, in the form of cold, dark filaments that slip silently and unobtrusively into the galactic disk, blending seamlessly into the existing cosmic environment. These cold streams are like quiet, persistent whispers of matter that nourish the galaxy from afar, ensuring its continued growth and vitality. Meanwhile, other streams of gas plunge inward in a much more energetic and tumultuous manner, arriving in hotter states as they undergo shock heating upon entering the galaxy's domain. These hotter inflows often radiate their presence through ultraviolet light or even X-ray emissions, illuminating the otherwise invisible currents that sustain the galaxy's evolution. These energetic, invisible rivers act as a physical and gravitational link to the universe beyond, connecting our galaxy to a much larger, more mysterious cosmos. Even today, the Milky Way continues to draw from these distant reservoirs of matter, sustained by the cosmic threads spun from the universe's earliest moments, allowing it to thrive and evolve over cosmic timescales. Within the galactic environment, hot gas bubbles periodically form, rising like chimneys from the disk of the galaxy into the surrounding halo. These bubbles are the aftermath of cataclysmic events, predominantly the explosions of massive stars and supernovae, which carve out vast cavities within the dense interstellar medium. When numerous supernovae occur in succession, their collective effects can generate enormous superbubbles, massive pockets of overheated gas that punch upward through the galactic disk. These bubbles effectively serve as natural vents, channeling energy, gas, and magnetic fields away from the galaxy's main plane and venting into the surrounding dark halo. They act as galactic chimneys, working like exhaust valves that regulate the internal pressure of the interstellar environment, dispersing heavy elements, metals, throughout the galactic halo, and influencing the large-scale structure of the galaxy's outer regions. In essence, the galaxy breathes, but not just through the gentle movement within its bright, swirling disk. It also exhales through these towering columns of hot gas and magnetic fields that carry energy and matter high above the galactic plane into the darkness of space, shaping its long-term evolution. While our galaxy appears tranquil and majestic in its visible light glow, emitting a gentle, luminescent band across the night sky, it actually radiates fiercely in other forms of electromagnetic radiation, particularly in high-energy wavelengths such as X-rays. The galaxy's core, home to a supermassive black hole and many collapsed stellar remnants like white dwarfs and neutron stars, are prolific sources of X-ray emission. These energetic phenomena illuminate the galaxy's more extreme and hidden aspects, revealing a universe far more dynamic than it seems to the naked eye. For instance, some white dwarfs and neutron stars exist in binary systems, where they siphon matter from their companion stars. As this material spirals inward and heats up to millions of degrees, it emits intense X-ray radiation, which can be detected across vast distances. Additionally, the halo surrounding the galaxy, composed of hot, diffuse gas, too emits faint X-ray signals, tracing the invisible, larger skeleton of our cosmic home. These emissions are impossible for our eyes to see directly, but are captured in detail by specialized telescopes. Instruments like Chandra and XMM Newton offer a radically different view than traditional optical observations, revealing a galaxy filled with extremes, regions of extreme temperatures, dense and collapsed remnants of ancient stars, and unseen radiation fields flowing through space. These high-energy images portray a galaxy not as a calm spiral, but as a realm of energetic phenomena, teeming with activity beneath its serene facade. Throughout the galaxy, a remarkable class of celestial objects called pulsars plays a constant and crucial role as cosmic clocks. Pulsars are neutron stars, the incredibly dense remnants formed when massive stars exhaust their fuel and undergo gravitational collapse. When these neutron stars spin rapidly, often hundreds of times each second, they emit beams of radiation from their magnetic poles, which sweep across space like lighthouse beacons. Due to their stability and precision, these pulsars act as extraordinarily reliable celestial timekeepers, their rhythmic signals reaching Earth in steady, predictable pulses. Astrophysicists utilize these cosmic clocks to measure vast distances within the galaxy, test the limits of gravitational theories, and even hunt for gravitational waves rippling through spacetime. These pulsars, remnants of stellar death, serve as a testament to the universe's capacity for order amid chaos. Utilizing arrays of radio telescopes, vast networks of antennas working in concert, astronomers have been able to map the intricate spiral arms that define our galaxy, carefully measure the subtle warp that ripples through the galactic disk, and uncover regions where stars are actively forming amid thick veils of darkness. In places where direct light from new stars and clouds of gas is obscured or blocked, it is through the penetrating gaze of radio waves that we can gain insight and see what lies hidden within the galaxy's depths. Unlike the visible light humans typically rely on, radio signals carry a different story, a language of sound and shadow that the galaxy whispers to those who know how to listen. Although we cannot hear this cosmic language naturally, science has developed sophisticated methods to interpret these signals, translating the universe's subtle cues into detailed images of shape, density, and shadow, revealing a universe rich with hidden phenomena. The story of our sun begins deep within the cradle of stars, presumably born as part of a large stellar nursery. Stars rarely emerge in complete isolation. They tend to form in groups, born from the same massive cloud of gas and dust that collapses under gravity's relentless pull, creating stellar assemblages known as clusters. It is almost certain that our sun was one such star, part of a closely knit family of hundreds, possibly even thousands of sibling stars, all shaped and born from a single colossal cloud. These clusters are like cosmic families, with stars formed together sharing a common origin. Over the billions of years that followed, the gravitational forces exerted by nearby stars, the passing of other celestial bodies, and the overall motion of the Milky Way itself gradually dispersed this original family. Many of the sun's siblings have since drifted far away from their original birthplace, each wandering along its own trajectory, influenced by the complex gravitational dance of the galaxy. These sibling stars now roam the galactic disk at different distances and directions, carrying with them subtle clues to their shared past, faint signatures embedded in their motion, chemistry, and age. Some of these celestial relatives might still be hiding among countless other stars, their connection to us concealed in the vast darkness of space. They are, in essence, lost family members scattered throughout the galaxy, remnants of the same ancient cloud of material that once birthed our star. In the ongoing quest to identify these long-lost relatives, astronomers are turning to extensive surveys such as Gaia, a European Space Agency mission that maps the positions, movements, and characteristics of over 1 billion stars, along with many spectroscopic databases that analyze the light from stars to discern their chemical compositions. By comparing a star's age, motion, and precise chemical fingerprint, scientists hope to piece together the genealogy of the Sun's original cluster. Although concrete identifications are still emerging, a handful of candidates have already surfaced. Stars whose shared origins from the same cloud of enriched gas are supported by their similarities in chemical makeup and motion. If these stars are indeed the Sun's siblings, unlocking their secrets could provide invaluable insights into the conditions and environment in which our star and the early solar system took shape. Our specific location within the galaxy, therefore, is not entirely a solitary point in space. Somewhere out there, in the vastness of the Milky Way, the ancient kin of our Sun might still shine, hidden amid thousands of other stars, but connected through a shared history rooted deep in cosmic time. Meanwhile, the structure of the Milky Way itself is continually influenced by its dynamic motions and gravitational interactions. The galactic disk, its prominent flattened plane, does not maintain a perfectly smooth or static shape, but exhibits gentle wobbles and ripples that traverse it as the galaxy spins. This phenomenon, known as the galactic warp, is most evident in the outer reaches of the disk, where it bends upward on one side and dips downward on the other, creating a subtle but unmistakable curvature. The origin of this warp is still a subject of active research. Possible causes include the gravitational tug of nearby dwarf galaxies, interactions with elusive dark matter, or internal asymmetries within the galaxy's mass distribution. This warping is akin to a vast, slowly oscillating wave that travels through the stellar fabric of the galaxy. From our vantage point on Earth, these motions are imperceptible to us in real time. Yet from a cosmic perspective, the Milky Way is more than just a serene, flat spiral. It's a breathing, undulating entity, curving gently as it completes its endless rotation. This dynamic motion influences the structure and behavior of the galaxy's components, including star clusters and stellar streams. Long, faint trails of stars that have been tugged and stretched by the galaxy's gravitational tides over time. The gravitational forces exerted by the immense mass of the Milky Way act much like a colossal, invisible hand pulling on everything within its domain. Just as the moon's gravity causes ocean tides on Earth, the galaxy's own gravitational field creates tidal forces that reach out to stir up and distort groups of stars, satellite galaxies. One might naturally assume that we possess a precise understanding of the total mass of our own galaxy, the Milky Way. After all, it is our cosmic home, and we are surrounded by countless stars and clouds of gas that seem, at first glance, to offer clues about its weight. However, in reality, measuring the galaxy's true mass proves to be a task of extraordinary complexity and difficulty. The reason for this is that the visible matter, those luminous stars and diffuse clouds of gas, constitutes only a small fraction of the entire mass. The remaining bulk is concealed within an enormous, invisible dark matter halo that enshrouds the galaxy, creating a gravitational framework that holds everything together. This halo is made up of mysterious, non-luminous particles that do not emit or absorb light in any detectable way. rendering it inaccessible to direct observation. Because of this, astronomers have had to rely on indirect methods to estimate the galaxy's total mass, methods that inevitably come with a significant degree of uncertainty. When scientists attempt to calculate the Milky Way's mass, they look at how fast stars orbit far from the galactic center. These measurements are crucial because the speed of a star's orbit provides vital clues about the gravitational pull exerted by the entire galaxy. Yet, this task becomes increasingly complicated at vast distances where data is sparse, and the influence of dark matter, which does not interact with light, adds an extra layer of complication. Different studies and models produce a broad range of estimates. Some suggest that the Milky Way weighs in at around 1 trillion times the mass of our Sun, while others propose significantly higher figures, pushing the galaxy's mass to even greater extremes. The core challenge lies in the fact that the remote stars we observe are only a small sample, and the true distribution and density of dark matter remains largely elusive. As a result, the precise weight of our galaxy continues to be an open scientific question, a quiet, persistent mystery that almost beckons curiosity and further investigation. Despite being our immediate cosmic environment and the galaxy we call home, the actual mass of the Milky Way remains shrouded in uncertainty and debate. Interestingly, for many years, astronomers believed that the neighboring Andromeda galaxy, which appears both slightly larger and brighter to observers from Earth, also outweighed the Milky Way in terms of total mass. This assumption was based on observations of their relative sizes, luminosities, and the dynamics of their mutual motion through space. It was widely held that a galaxy of greater brightness and apparent size should also be more massive, leading to the conclusion that Andromeda was the more heavyweight of the two Roman celestial cities. However, recent advances and more refined measurements have begun to challenge this long-standing view. New data suggests that the dark matter halo enveloping our galaxy might be more extensive and denser than astronomers previously believed, meaning the Milky Way could be quite a bit heavier than once assumed. If this hypothesis holds true, then our galaxy, modest and unassuming in appearance, might actually surpass Andromeda in total mass, despite its less flamboyant luminosity. Such a reversal has profound implications, not only for how we compare these two giants, but also for predicting what will happen in the distant future. When the Milky Way and Andromeda eventually move closer and collide, a dramatic event predicted to occur in perhaps 4 billion years. Their masses will play a vital role in shaping the nature of their grand merger. The dance of gravitational attraction and the resulting dynamics will be profoundly influenced by the true ratios of their weights. In this cosmic collision, the existing mass distribution will determine the relative speeds, the distribution of stars, and the formation of new structures. Beneath its seemingly tranquil spiral facade, the Milky Way conceals a weight and complexity that surpasses what many once assumed. Although its spiral arms shimmer with calm beauty, they hide a mass and gravitational influence that are still being unraveled by scientists. In this quiet galaxy, there exists a weight of multiple trillions of suns, a silent force shaping the cosmos and the future of our own galactic neighborhood, all but hidden behind the veil of dark matter and the limits of our current observational techniques. Turning our gaze to our galaxy's immediate environment, we find the large and small Magellanic Clouds. two bright and conspicuous satellite galaxies visible from Earth's southern hemisphere. For many centuries, astronomers believed these luminous clouds were long-standing companions orbiting the Milky Way, caught in a gracious celestial dance around their larger host. Their positions, motions, and apparent proximity seemed to confirm that they had been gravitationally bound to the Milky Way for a significant amount of cosmic time, serving as enduring witnesses to our galaxy's gravitational domain. However, recent evidence has begun to challenge this traditional view. New measurements of their velocities and movements through space suggest that these clouds may be relatively newcomers, captured only in recent cosmic history. In other words, they might be recent arrivals rather than ancient companions, making their first close approach to the Milky Way in a cosmic sense. If there are tangible, almost palpable signs that the universe we observe is not a static, unchanging entity, but rather an ever-evolving cosmic tapestry constantly reshaped by the unpredictable currents of its own history. Among these subtle yet profound hints are immense, ghostly structures, vast shells composed of glowing gases that serve as remnants of ancient, intense star-forming episodes. When astronomers gaze across different regions of our galaxy, the Milky Way, they have uncovered enormous spherical shells of interstellar gas, some stretching across hundreds of light years. These enormous bubbles are the silent witnesses of violent, energetic events known as starbursts, periods during which clusters of massive stars formed in rapid succession, illuminating the galaxy's dark depths with their brief but brilliant lives before ending in spectacular explosions. During these energetic episodes, the combined force of stellar winds, powerful flows of charged particles, and supernova explosions carved out enormous cavities in the surrounding gas and dust, effectively blowing material outward in all directions. Over vast stretches of cosmic time, these expanding shells gradually slow down, their momentum decreasing as they blend into the interstellar medium, yet they never quite vanish. Instead, they linger as ghostly, luminous bubbles, silent markers of the galaxy's once fiery birthplaces and death zones. These remnants are the fossils of cosmic fireworks, their faint, cold echoes whispering stories of the galaxy's vibrant past and reminding us that even in the silence of space, the history of intense stellar activity persists, etched into these distant, glowing membranes. Meanwhile, in regions where stars are densely packed, such as the cores of globular clusters, occasional stellar encounters can become dramatic, sometimes culminating in direct collisions. The vast stretches of space seem immense and empty at first glance, with stars appearing as tiny points of light. Still, in these crowded stellar neighborhoods, the sheer proximity of stars allows for close approaches and interactions that are rare but entirely possible given enough time. During such an encounter, two stars might pass perilously close, their mutual gravity pulling them into a collision or merger that can produce startling phenomena. The resulting fireworks might include an intense burst of light, a spectacular collision that merges the two suns into a brighter, larger star, or the creation of a rare star known as a blue straggler, seemingly younger and more luminous than its neighboring stars, an anomalous newcomer in an aging stellar population. These events, though infrequent, are not impossible, and given billions of years, the most tightly packed star clusters can continually undergo such rearrangement, rarely but inexorably changing their stellar makeup through chance and gravity's subtle hand. In addition to individual stellar collisions, the dense environments of the galaxy's core and other crowded regions serve as theaters for the disruption of binary star systems, pairs of stars gravitationally bound in a shared orbit. Many stars are born in binary or multiple systems, drifting through space in close companionship. However, just as friendships can be broken, so too can these cosmic bonds be torn apart under the right circumstances. When a binary system ventures too close to the supermassive black hole at the galaxy's core or traverses through a densely packed cluster, the immense tidal forces exerted on it can cause the pair to break apart. One star might be flung outward at incredible speeds, escaping the galaxy's gravitational pull entirely, becoming a rogue star, an independent traveler wandering through intergalactic space. Meanwhile, its partner could become gravitationally captured by the black hole or cluster, either settling into a new orbit or being slowed down so much that it remains in the vicinity. In some cases, the companion star is ejected with enough velocity to escape the galaxy altogether, transforming into an intergalactic drifter, racing through the dark void beyond the confines of the Milky Way, carrying with it the faint memory of its once shared history. These dramatic disruptions of binary systems generally happen quietly, unnoticed by observers from afar, as the forces at work are often subtle and happen over long timescales. It is a quiet and inexorable process, an ancient tearing apart of long-standing bonds driven solely by gravity's relentless influence. In the larger tapestry of cosmic events, some stars, having gained enough velocity from such interactions, achieve escape velocity that surpasses the galaxy's grasp, over 500 kilometers per second, and are inevitably cast into intergalactic space. These hypervelocity stars are exceedingly rare but undeniable existence. Some are believed to have been expelled by gravitational interactions with the galaxy's central supermassive black hole, while others might owe their high speeds to complex gravitational slingshot effects during three-body encounters or to the explosive force of a supernova in a binary system. Once liberated from their former stellar associations, these stars become solitary wanderers, drifting alone into the vastness of intergalactic space. They function as tiny cosmic lighthouses, their faint glimmers traveling across the dark void far beyond the galaxy's spiral arms. Each of these stars carries with it a delicate remnant of the galaxy's history, a faint echo of the tumultuous processes that in the vast expanse of our galaxy and beyond, there are celestial travelers known as intergalactic wanderers, which are often observed following peculiar and elongated orbits far removed from the main disk of the galaxy. Instead of moving along familiar paths within the densely packed regions, these mysterious objects traverse the distant outskirts or the faint, diffuse halo that borders the visible part of the galaxy. Their paths are unusual because they seem to take detours through regions where the density of stars and matter is much lower. Yet their unique motions and compositions allow astronomers to identify them. These stars do not conform to the typical patterns observed in the local stellar neighborhood. They stand apart, almost like cosmic immigrants from other environments, bringing with them stories, histories, and chemical signatures that hint at origins outside the familiar galactic plane. Much like travelers from distant worlds, these stars carry with them clues to processes and regions that we have yet to fully understand, making them invaluable to our comprehension of the galaxy's structure and its dynamic history. It's important to recognize that the Milky Way is not a closed or isolated system. Rather, it is a vibrant, living mosaic, continuously shaped and reshaped by the passage of time and the motions of countless stars, gas, dust, and other celestial bodies. Within this intricate system, there exists a fascinating process often called the galactic fountain, a cycle of gas that moves between the galaxy's bright, dense disk and its surrounding halo. This process involves a quiet but essential exchange of matter, occurring both above and below the main plane of the galaxy. Gas is often heated and pushed outward into the halo by energetic events such as supernova explosions and intense stellar winds, which stir and energize the surrounding medium. Over time, this heated gas cools, condenses, and gradually begins to rain back down onto the galaxy's disk, completing a slow, cyclical journey that spans millions of years. This continuous motion acts as a vital mechanism for stirring the interstellar medium, the vast, diffuse material that fills the space between stars. It's also instrumental in redistributing heavier elements created within stars, thus influencing the chemical composition of future generations of stars and planets. Moreover, this process plays a significant role in regulating star formation, ensuring the galaxy's ongoing evolution. Think of it as a kind of cosmic respiration, an invisible, rhythmic breathing motion that keeps matter flowing between the densely populated galactic plane and the expansive halo, like the inhale and exhale of a living organism. Far from being simply a rotating system, the galaxy actively circulates matter, exhaling and inhaling in an elaborate dance that has sustained its structure over immense spans of cosmic time. It's a process of dynamic renewal, vital for maintaining the balance and vitality of the galaxy's complex ecosystem. Delving deeper into the materials that comprise our galaxy, we find tiny dust grains that carry within them organic compounds, complex molecules based on carbon atoms. Within the dense clouds of interstellar dust, the faint, drifting particles between stars, scientists have identified a rich variety of these organic molecules, which include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and other complex carbon-based compounds. Although these molecules are not alive in themselves, they are chemically intricate, and their origins can be traced back to the atmospheres of dying stars, or within cold, dark clouds, where radiation transforms simple substances into more complex ones. These minute grains are not static. They are carried across vast distances by the force of galactic winds, powerful streams of particles that spread from one region of space to another over light years. Eventually, they settle into the gaseous material from which new stars and planets are born. In some cases, these tiny organic-rich grains may have fallen onto the early Earth, potentially seeding it with the initial building blocks of life. As such, interstellar dust is not merely cosmic debris or meaningless detritus. It is, quite profoundly, a cargo of potential, silently drifting through the darkness of space in search of a hospitable environment. These interstellar clouds, filled with gas and dust, serve as the cosmic nurseries where new solar systems and planetary bodies originate. When these clouds collapse under gravity to form stars, they also create the conditions necessary for planetary systems to develop. Remarkably, these emerging planetary systems often inherit the chemical fingerprints of their parent clouds, carrying with them the essential ingredients for life: water, organic molecules, and other complex compounds. If such regions contain these vital elements, they may end up incorporated within comets, asteroids, or planets, thus acting as delivery mechanisms for prebiotic materials. In some parts of the galaxy, the richness of this prebiotic chemistry appears particularly pronounced, suggesting that conditions conducive to the development of life are more common than previously thought. Although scientists are still working to understand just how widespread life might be in the universe, the existing evidence hints that such favorable environments arise naturally and often. It is conceivable that the seeds of life are scattered across the galaxy, embedded deep within its coldest and most, their internal structures and the evolutionary paths they follow stand apart, each unique in its composition and development. While the lifespans of these celestial entities may often be relatively short on cosmic scales, fleeting though they might be, they shimmer and twinkle with a mesmerizing intensity during their brief existence, much like haunting sirens singing their songs in the vast darkness of space. The galaxy itself is tilted at an angle relative to the plane of Earth's orbit, creating an intriguing geometric relationship. From our vantage point on Earth, the Milky Way spills across the night sky as an elegant, shimmering ribbon of light, gracefully arcing from horizon to horizon. However, this luminous band does not align directly with the plane of our solar system. Instead, the galactic plane, the vast, relatively flat disk that hosts the majority of the galaxy's stars, is inclined sharply, approximately 60 degrees, relative to the ecliptic, the imaginary path traced out by the Sun and planets as they orbit the center of the solar system. This pronounced tilt is why the Milky Way appears at an angle in our night sky, shifting its position notably with the changing seasons. We are integral, yet slightly offset, constituents of this grand galaxy, a tiny system of our own, subtly skewed within the broader cosmic whirl. Visualize the galaxy as a vast, spinning ocean, with our smaller system drifting like a tiny tilted boat upon its shimmering surface. Within the halo that surrounds the galaxy's bright, luminous disk, some remnants of stars are surprisingly ancient, predating even the galaxy's dense, disk-shaped structures. Among these faint, distant stars are white dwarfs, those cooling cores of once bright stars, now quietly fading over billions of years. Remarkably, astronomers have identified white dwarfs that are older than the galaxy's thin, luminous disk itself, preserved as fossils of an earlier epoch. These relics formed during the galaxy's youth, before its core and major structures had fully settled into their current configurations, serving as silent witnesses to the galaxy's formative years. The presence of such ancient stellar remnants suggests an era long before the galaxy reached maturity, a period when star formation was still intense, and the universe was still forging its luminous fabric. These cores, cooling slowly over cosmic time, carry with them the echoes of a bygone era, etched into the outer halo as quiet testament to the galaxy's deep and complex history. The galaxy's bright, bustling disk may dazzle within our view, but the halo keeps alive the memory of times far earlier, when the galaxy was only beginning to take shape. Beyond the luminous core and sprawling spiral arms lies a realm inhabited by the galaxy's most distant stars, orbiting far beyond the bright, familiar structures we often associate with the Milky Way. These stars are located tens of thousands, or even hundreds of thousands, of light years away from the galactic center, wandering through the vast halo on slow, expansive trajectories. Each star's journey around the galaxy takes billions of years to complete, a testament to the immense scale of cosmic time and space. Many of these distant stars are thought to have been captured in past galactic collisions or mergers, drifting in the galaxy's outermost regions like distant sentinels, remnants of galactic encounters that have been absorbed into the halo. These stars are faint and sparse, yet they serve a vital role. They help astronomers understand the overall size and shape of the galaxy, as well as the reach of its gravitational influence. The Milky Way, in truth, extends much further than the bright, visible structure we so often admire. Its tendrils reach into the darkness, shaped and molded by stars and remnants at its very edges, which continue to influence its overall dynamics. The shape of the Milky Way itself is subtly asymmetric. Although commonly depicted as a perfect spiral with symmetric arms, the real galaxy is more of a living, breathing entity, lopsided and irregular in several fundamental ways. One side of the galactic disk is noticeably thicker than the other, and the spiral arms display variations in brightness and length that add to its uneven appearance. Even the stellar halo, a faint and diffuse region surrounding the main disk, is slightly shifted from the galaxy's center. These asymmetries likely arise from gravitational interactions, perhaps from nearby dark matter clumps, dwarf galaxies, or remnants of past mergers. The galaxy is far from a static, symmetrical pinwheel. Rather, it is a dynamic, evolving structure, marked by tugs, twists, and distortions that resemble a spinning dancer whose flowing skirt has been caught by an unseen breeze. Its beauty lies precisely in this irregularity, in the graceful yet imperfect imbalance which has been sculpted over billions of years by the ceaseless forces of gravity and cosmic evolution. Astronomers carefully map these intricate structures using various types of variable stars. Particular stars pulsate with a regular rhythm, their brightness ebbing and flowing in a predictable cycle, expanding and contracting like slow, luminous heartbeats echoing through space. These variable stars, including well-studied by carefully observing the amount of time a star takes to fluctuate in brightness, its period of brightening and dimming, astronomers unlock critical information about the star's intrinsic luminosity. This measurement, when combined with the star's apparent brightness as seen from Earth, enables scientists to calculate the star's true distance from us. In essence, these stars serve as celestial benchmarks, nature's own measuring sticks scattered throughout the universe. They help us comprehend the vast scale of our cosmos by providing a means to measure the spatial dimensions of the Milky Way galaxy. These luminous beacons act as glowing markers across the darkness, allowing us to chart the galaxy's shape, size, and structure with increasing precision. They illuminate the positions of various features within the spiral arms, helping us understand the galaxy's overall layout and scale, a grand cosmic map that unravels piece by piece. Thanks to these stellar yardsticks, astronomers can sketch a more accurate three-dimensional picture of the Milky Way. The process involves comparing how bright a star appears to us with how luminous we know it truly is. This comparison reveals how far away the star must be. In this way, these stars serve as fundamental anchors in our quest to grasp the true proportions of our galactic home. They are like cosmic signposts, bright, consistent, and reliable, that guide us through the complex architecture of the galaxy. This method of measurement is crucial for understanding not only the galaxy's three-dimensional shape, but also its history and evolution over vast periods of time. The ongoing efforts of space missions, particularly the Gaia project, led by the European Space Agency, have dramatically transformed our knowledge of our galaxy. Launched with the aim of creating the most detailed and accurate map of the Milky Way ever assembled, Gaia is revolutionizing our understanding by collecting extensive data on the positions, movements, and brightness of more than 2 billion stars. This immense data set is like an astronomical census, providing an intricate, three-dimensional view of the galaxy that includes the motions of stars, the distribution of stellar populations, and the overall architecture of the galactic system. By mapping stars in such detail, Gaia reveals the dynamic nature of the Milky Way, showing how it shifts and evolves through cosmic time. From its comprehensive data, Gaia has uncovered a wealth of surprising features within the galaxy. For instance, it has detected streams of stars that originate from the remnants of smaller galaxies, which were swallowed in past mergers. It has also created detailed maps of the warp and ripples in the galactic disk, distortions that tell the story of past gravitational interactions. Moreover, Gaia's observations allow scientists to trace the Sun's orbit within the galaxy with remarkable precision, providing insights into the solar system's journey through the Milky Way's vast and intricate landscape. Each new release of Gaia's findings peels back more layers of mystery, gradually transforming what once appeared as a vague cluster of fuzzy light into a sharp, vibrant, and dynamic map of our galaxy, a living, breathing universe that continues to surprise and awe us. One of the most striking features of the galactic structure is the dense, luminous band known as the galactic plane. On a clear, dark night, far from city lights, this feature looks like a faint, hazy river of stars stretching across the sky, flowing through the darkness overhead. This isn't just a simple line in the sky, but rather a broad, flattened band, a three-dimensional plane where the majority of the galaxy's stars are concentrated. This band is the thickest part of the Milky Way's disk, a vast, flattened region filled with countless stars, interstellar dust clouds, and regions where new stars are actively forming. When we gaze along this plane, we peer through the galaxy's most crowded corridors, where the star density is highest and the cosmic activity is most intense. Far more than just a beautiful feature, the galactic plane embodies the bustling, energetic heart of the Milky Way. It is where densely packed star clusters thrive, where dust clouds cocoon regions of ongoing star birth, and where the life cycle of stars, their creation, evolution, and eventual demise, plays out at a frenzied pace. From our vantage point on Earth, nestled far from the galactic core, we look out along this dense plane, witnessing the universe's vibrant activity in a narrow slice of the galaxy. This region encapsulates the chaos and order of our cosmic neighborhood, serving as the bustling, humming nucleus where most stars are born and die. The brightest part of the night sky is directed toward the inner core of the galaxy, an area densely populated with stars and shrouded in clouds of dust and gas. The Milky Way's center resides roughly in the direction of the constellation Sagittarius, which appears as a bright, glowing patch, thick with stellar density and cosmic dust. From our perspective on Earth, however, we cannot observe the core directly with visible light because dust clouds obscure our line of sight, preventing us from seeing the brilliance and activity at the very heart of the galaxy. Nonetheless, this central region still shines strongly. Even with the most advanced and sensitive instruments we have developed, capable of capturing astonishing details, our glimpse into the vast and intricate universe that is the Milky Way remains only a fragment of the whole. The tremendous dust clouds that permeate our galaxy act like cosmic veils, obscuring the true scale and grandeur of its many components. Meanwhile, phenomena such as motion itself, whether the swirling rotations or the subtle drifts, are often concealed within silence, hidden from direct observation, waiting to be interpreted through careful measurement and deduction. Out beyond the luminous stars that mark the galaxy's glowing arms, dark matter vastly outnumbers these bright celestial bodies, composing the elusive and mysterious substance that shapes the structure of the universe rather than shining within it. Between each star lies stretches of seemingly empty space, yet these regions are far from being void of meaning. They are points of potential, grounds where new worlds might someday form, where particles drift in silent anticipation of creating something spectacular. The Milky Way, therefore, extends far beyond what our eyes can see or what our instruments can detect at present. It is not merely the glowing band of light stretching across the night sky that initially captures our attention. It is also the realm of possibilities, the realm of what we suspect and what we infer based on scientific clues, the universe's silent secrets that beckon us to unravel. Our curiosity about this galaxy is born from both what we observe and what we imagine, fueling our desire to comprehend its ancient light, the birthplaces of future stars, among drifting worlds, as well as questions that still remain unanswered or partially understood. Inside that immense and mysterious cosmos, all around us, are storied remnants of cosmic history, a history that includes ancient light that has traveled millions or even billions of years to reach us, as well as the ongoing formation of new stellar bodies. Within this expansive universe, planets are drifting gracefully through space, their orbits quietly traced by gravity, while nascent suns ignite in vast stellar nurseries. Deep within the galaxy's spiral arms, we have looked upward and inward, observing the glowing heart of the galaxy shining through a veil of dust, revealing the core of this cosmic ocean. Our own existence is intertwined with all of this grandeur. We are not merely passive spectators. Rather, we are active participants in the unfolding story of this galaxy, sharing in its luminous journey through time. The elements forming our very bodies, such as the iron in our blood, were forged in long-vanished stars that burned brightly in the distant past. The oxygen we breathe was created in ancient cosmic explosions, dispersing essential elements across the cosmos. The atoms that make up our bodies trace their ancient origins back to the earliest moments of the universe, born from the same matter that now fuels the shining stars overhead and whispers quietly through clouds of interstellar dust. Tonight, as you rest, the galaxy continues its silent, majestic rotation. Stars are still forming. Light is traveling across cosmic distances, and silent orbits persist in their eternal dance. You find yourself floating within this grand, luminous realm, a small point of warmth amid the vast darkness, nestled within a spiral arm of this quiet, radiant sea of stars. If, by any chance, your thoughts are still awake and lingering in the quiet hours, you might consider the next chapter of this cosmic story unfolding beyond your awareness. As you prepare to drift into sleep, I wish you peaceful dreams filled with gentle wonder. May your night be calm and your mind tranquil, safe in the knowledge that the galaxy continues its age-old voyage, silently weaving the fabric of cosmic history around you. Sleep well, and let your mind drift softly into the depths of the universe's endless mysteries. Good night.